Hello, everyone. This is Matchgate benchmarking, scalable benchmarking of a continuous family of many-qubit gates. The paper on which this talk is based can be found in the archive here, and this is a collaborative work with Sepehr Nezami, who is at Caltech, Matthew Riga, who is at Rigetti, and Michael Walter, who is at the University of Amsterdam. So what are we going to talk about today? Well, the first thing I want to do is give you a little bit of sort of background, and this background particularly has to do with a protocol called randomized benchmarking. Now, randomized benchmarking is probably the standard way for an experimentalist to learn something about the quantum operations that they have in their quantum computer, in particular learn how noisy they are. So randomized benchmarking is a generic tool that allows you to estimate average fidelities of quantum gates, and in particular averaged over some set of gates. And usually this set will be a group, for concreteness, we can always imagine this to be the Clifford group, which is sort of the standard gate set you would do this with. And randomized benchmarking has been around for around a decade, and the reason it has sort of endured and become really popular is because it has a lot of really neat properties. The first one is that it is efficient, and by this I mean that it doesn't become exponentially hard to do either in computational complexity or in sample complexity as you scale up the number of qubits in your device. Both of these parameters are bounded polynomially somehow with the number of qubits, which is nice. It's sort of a nice contrast with something like tomography, which does scale exponentially in the sample size. It's also something called spam error resistant, where spam is short for state preparation and measurement. And this is sort of a neat property because it's nice to be able to separate errors that are due to gates and errors that are due to like state preparation and measurement. And in particular, this is nice because gate errors tend to be a lot smaller than state preparation and measurement errors in practice. And the last thing, which is sort of important for us, is that randomized benchmarking has a really well-developed theoretical framework. It works under a broad sort of variety of error models, and lots of aspects of this system have been sort of very well studied. Now, I've told you what it does, and now I need to tell you what it is. So randomized benchmarking as a protocol is actually very simple. So it's sort of encapsulated in this one figure. So what you do is you prepare some starting state, usually the all-zero state, and it doesn't really matter how correctly you do this because, again, spam error resistance. And then what you're going to do is you're going to sample at random, because there's an average here, G1 to GM gates, so M gates circuits from your set of circuits, which again you can think of as a Clifford group, and you're going to apply them to your state. And then you're going to take the descriptions you have of all these circuits and compute as compact as you can an inverse of this G1 times GM so that the overall sequence is the identity. And this gives rise to sort of the first property that you need for your gate set. One, that it's probably going to be a group, so you always have a nice notion of inverse. And two, that this thing can be classically computed. So you need some sort of group of gates that is classically tractable, and this will come back later. And then you do usually a two-component measurement, so I'm only showing one component here. This also doesn't matter all that much. And then you do this for lots of random sequences, ideally for all of them. You get this sort of average of length m, and then you sort of compute this average b of m. And if everything works, this b of m should depend sort of nicely in an exponential manner on this sequence length m. And it turns out this sort of depends on the gate set, but for the Clifford group, this is exactly true, that this is precisely a single exponential under reasonable experimental conditions. And from the decay rate of this from the decay rate of this exponential, you can calculate the average fidelity of your gates, sort of averaged over your gate set. And that's what we want. And this is a really nice protocol. And it works beyond the Clifford group for a whole bunch of different gate sets and a sort of a wide theory. And basically our goal is to sort of take this and expand upon it. And we're going to expand upon it in a particular direction. Namely, we are going to want to talk about continuous gate sets. And this is something that hasn't really been done before. So RB thus far really only applies to discrete gate sets. And if you want to do something with continuous gate sets, sort of a separate set of problems shows up. But why would we care about continuous gates at all? Well, they're very useful. So things like VQA and QAOA and other NISCI applications all make use of these sort of continuously parameterized circuits. And also many natural gates in quantum computing platforms actually have like a free parameter. So they're really rotations in some space. And it's good to be able to exploit that to its fullest, especially in sort of the limited quantum computational realm that we are in now. So it would be nice to do randomized benchmarking for at least a sort of relevant continuous gate set, which is something that hasn't really been done before. And that's sort of what we're going to try and do today. And to do that, we need to do two things. One, we need to find a continuous gate set that has the correct properties, and that is also sort of not too contrived. It's sort of experimentally relevant and also has the properties that you need for randomized benchmarking. And then two, prove that if you plug in this gate set that randomized benchmarking still works, or if that fails, to sort of adapt randomized benchmarking to work for you with this particular gate set. So that's what we're going to do for the rest of the talk, basically. And we're going to start with step one, and then we're going to go to step two. So step one is find a continuous gate set. And the example that we're going to use is sort of, I think, the canonical continuous gate set. But what do we need what do we need for randomized benchmarking to work is we need a gate set that has a few interesting properties. We need it to be continuous, because that's the premise of our plan. And we also need it to be classically simulable, because we need to be able to compute these inverses. And then thirdly, we need it to be what I would like to call a good randomizer, in the sense that it sort of spreads out quantum states over the Hilbert space well. And I'm going to get into a little bit more technical details on that later. And we want it to be compilable into 1 and 2 qubit gates. And this is sort of an argument that it shouldn't be a contrived object that people can't actually implement. Now it turns out such a thing exists, and this is actually kind of nice, and I want to break a lance for these things, and they're called matchgates. And matchgates are a really cool sort of continuous analogon to the Clifford group in some sense. And they've been around for about 20 years, potentially longer if you think about it. And they are the group of n-qubit gates generated by sort of 2-qubit XX and YY rotations, so rotations around these axes. It's important that you have them only nearest neighbor on a line, otherwise it doesn't work. And single qubit Z rotations. So you take these things and sort of you take whatever closure you get of that, and that's the set of the group of match gates. And it turns out that these are classically simulable. So this sort of infinitely sized group that acts on an n-qubit space is classically simulable sort of in polynomial time in the number of qubits on a classical computer. And this was proven in 2000 by Valiant for a completely different reason. And then the reason why, at least in my head, was given in a beautiful paper by Terhal and DiVincenzo, where they argued that these sort of matchgate evolutions are in fact generated precisely by sort of non-interacting fermion evolution, so n fermions that don't interact. And sort of mathematically, it'll turn out that this is exactly a spin representation of the special orthogonal group, SO2n, where n is the number of qubits. And this will be useful later for randomized benchmarking. And also, because it's SO2n, everything is decomposable. And there's many ways to do it, and one way is sort of Gibbons rotations. We give another way in the paper, but this is something that you can exactly do. So this is sort of our gate set, and we're going to work with this. Oh, I want to also point out that these XX and YY rotations, they're sort of very natural gates. For instance, if you were in an ion trap computer, but also if you have, if you're doing superconducting circuits, you often have gates that are sort of like this. And we'll see an example of this all the way at the end of the talk. And we want to add one more thing to the match gates, which is this orthogonal bit here. And the reason for this is sort of technical. And basically the reason is that match gates, as they are, they conserve parity. And this is kind of annoying. It sort of clashes with this good randomizer idea. So we're going to explicitly add something to our gate set that breaks parity, and we're going to do that in the simplest possible way. We're going to add a single qubit X flip to our gate set, And mathematically what this does is lifts the match gates to a sort of a larger gate set that is precisely a spin representation of the orthogonal group. So you sort of get rid of this determinant condition. It's still classically simulable, sort of trivially by the same argument. And it has slightly better randomization properties because it breaks explicitly parity, so it doesn't conserve the parity of any computational basis state necessarily. So that's our gate set, and I've sort of hopefully argued that it's useful. Now, step 2 is, can we apply randomized benchmarking? And the first thing we need to sort of think about is, why does randomized benchmarking work in the first place? And in particular, why does it work for the Clifford group? And it turns out that the reason it works is essentially representation theoretic. So if you take the Clifford group and you take sort of its standard representation on density matrices, so the conjugation representation, so G dagger acting on a matrix, this thing decomposes exactly into two irreducible representations, one trivial one and one everything else. And sort of the physical consequence of this is that averaging over the Clifford group turns everything exactly into a depolarizing channel. And this means that if you do this sort of m-fold average with an inverse, what you're really doing is creating m compositions of a depolarizing channel, which means it's sort of obvious that this becomes well described, this mean, by a single exponential decay with some offset that you don't care about. And then this p here is a depolarizing parameter, which you can sort of map to the average fidelity. But the point here is that this has two irreducible representations. And this is because the Clifford group is a 2 design. It randomizes really well. Now, it turns out that for the orthogonal Matchgate group, the same thing is not true. If you look at the same representation, you don't get two irreducible representations. You get 2n+1 irreducible representations. And you could say, okay, this isn't a problem. We can still do randomized benchmarking, where instead of averaging over elements of the Clifford group, we sort of randomly pick elements from the Matchgate group or the orthogonal group on 2n of size 2n, and just do the same thing. Apply the sequence, compute the inverse, which you can do classically, measure, state prepare. And it turns out that you still get something. Like this average here is not described by a single exponential, which you would expect from the Clifford group, but instead, because of this representation theoretic structure, you get something that is described exactly by 2n+1 exponential decays. And it's important here that this thing here, this average, this B of m, is something you can still estimate efficiently, even though these are integrals, because these are all probabilities, they're sort of numbers between 0 and 1, and you're taking an average of them. This average actually converges really quickly just by some standard Chernow bound. The problem, however, lies in the fitting of this thing. So say you want to compute all of these lambdas, which is really what we're after. Then you need to take different B of m's for different m's, and then you want to fit this sort of linear combination of exponentials to it. However, for the problem is that this fitting process is actually exponentially hard in the number of exponentials. And in practice, this is just a really mean and ill-conditioned fitting problem. So for more than 2 qubits, it's already basically impossible with a reasonable amount of data. So sort of standard randomized benchmarking, even though you can estimate these averages efficiently, it sort of fails because you can't do the fitting properly. Now, of course, we didn't give up here. We said, okay, if standard RB doesn't work, we're just going to change the randomized benchmarking protocol. And it turns out there are sort of very good ways to do this, and I'm going to talk about these ways in a little bit more generality in my other randomized benchmarking talk, which you can go watch. And this is through something called correlation functions. And these are actually, they're moderately complicated objects, but the only thing you have to remember about them is that they're a function of the sequence of gates that you're going to do, and one of these representations. In particular, you're going to sort of simulate the projector onto one of these representations after you do the gates. And this is something that it turns out you can actually still calculate efficiently on a classical computer. So you can compute these numbers. So what we're going to do is we're going to take randomized benchmarking, and instead of doing this average here, we're going to not do the average at all, but we're going to compute these correlation functions and plug them in instead. So we're going to do some random average correlated with this function that's also a function of this sequence. And for technical reasons, we're also going to measure in the entire computational basis instead of a two-component POVM. But you can sort of forget about this. It's not super important. And it turns out that this thing, this average, this BK of M, by this sort of projection property, is actually described by a single exponential. So you can, if you have all of these BK of M sort of exactly, or good estimates of them, then you can fit your lambdas and you're happy, because now you just have n sort of tractable problems instead of one untractable problem. However, it's not so clear that you can still fit this, right? Because remember, our argument from before was that we were taking some average over essentially a bounded distribution, some uniform average over probabilities. But now we're taking an average weighted by these functions, and these functions, they're real numbers, but it's not so clear that they're actually bounded. And in fact, it turns out just that they aren't. So it's not so clear that even though you've solved the fitting problem, you have actually solved the, that you've created another problem, which is just now, how do you estimate these averages? And it turns out that this sort of vague Chernoff argument I gave before, it just absolutely fails, because these functions grow exponentially in the worst case with n. If you pick k to be sort of n as well, which you can, then this thing just grows exponentially in n. So it's not so clear that you can actually estimate the means for a fixed sequence length. However, we didn't give up here. You can try something more complicated, and that's what we did. So instead of just going from this boundedness argument, we went directly to saying, okay, can we just bound the variance of this thing? Because then we can construct an efficient estimator. So the goal is to say, okay, maybe the distribution is large, but the variance is still small, or at least polynomial in n and k. And this is a reasonably difficult mathematical problem, but it turns out after some work that this variance is upper bounded by a sort of special quantity which we call a moment integral. So here there's the variance, and then there's a max over 4 objects. So either t is 3 or 4, and this phi is either the all-zero state or the all-plus state for some technical reason. And then you have this moment integral, which is this big thing, times 2 to the t times n. So this is exponential in n. So what we want is that this moment integral as a function of t and phi, which is just this integral over the Matchgates weighted by some number, we want this thing to exactly cancel this 2 to the tn. We want this to be sort of polynomially close to 2 to the minus tn. And it turns out that this is the case, and you can compute it using some really cool sort of Lie group theory. And that's what I'm going to quickly show you now. So can we compute this moment integral? And I really think that this is sort of generally useful for other things as well. So I want to go over the argument. And I'm going to go over the argument precisely only for the 0 state, because for the plus state, it's a little bit more tricky, but it's essentially the same. So the argument goes as follows. We have this integral over the Matchgates, the orthogonal Matchgates, evaluated at 0 to the power 2t. So you're saying, aha, this U of Q is a spin representation of the orthogonal group. We already knew that. But then it turns out that the 0 state is precisely what is called a lowest weight vector of this representation, of one of the sub-representations, actually. But then it turns out if you take tensor powers of lowest weight vectors, which is precisely what you do here by taking this power, these are still lowest weight vectors. And this you get this from Lie algebra theory, is that means that this integral here is actually restricted to a single irreducible representation associated to this lowest weight vector. So then by Schur's lemma, you can compute this integral by just taking the trace and dividing by the dimension of the representation that you have overlap with. So the only thing that you care about is really the inverse dimension of this representation. And this, if you dig through sort of your Lie algebra book, you can actually compute it using something called the Wild dimension formula. And it turns out that this inverse dimension precisely grows as 2 to the minus Tn, which is again precisely what we want, times a polynomial in n, which means that the variance, which has this exponential, gets exactly cancelled, is polynomial in n, and t is either 3 or 4, so it's polynomial there as well, which means that the variance is bounded. So that's kind of cool, because it means that the protocol that we've given is scalable in sampling for a non-trivial reason. It's sort of fairly complicated that this works, but it works nonetheless. So now we have created a randomized benchmarking protocol that sort of rigorously works for orthogonal match gates. So we've done what we wanted to do with it, which is create a randomized benchmarking protocol for a continuous gate set. So of course we then went and actually implemented this in experiments. No, in particular Matt did, because he's someone that knows how to do this. So we went to Matt and asked him, hey, can you implement this protocol? I mean, he also did other things, and we did. So we on the Rigetti Aspen 8 chip, we performed 2-qubit matchgate orthogonal matchgate benchmarking. So it's a 2-qubit experiment, which means you get 5 exponential decays, which are the things that you see here, 0 through 4. And you can fit all of these 4 lambdas, and you can see that the variance is polynomially small. You can fit all of these things with reasonable accuracy, and you end up with a matchgate fidelity for like a matchgate circuit of 0.88, which is roughly consistent with earlier experiments that the people at Rigetti had done. So we were actually quite happy with this outcome, because it means that our protocol works. So yeah, so we've made our protocol, proved that it works, and then actually implemented it in an experiment. So what else are we going to do? Well, so we've got this matchgate benchmarking protocol, so we can characterize a good set of parameterized gates that we care about, and we get all the qualities of randomized benchmarking. We proved that it scales, so you can do it for a large number of qubits. It works as advertised on a Rigetti chip. And then there's some questions, right? So one thing is, are there other continuous classically simulable gate sets? Maybe. We don't really know, actually. I think this is actually a quite limited set. So one of the things you could do, which I think is a neat thing, is you can always sort of conjugate your matchgate set by a Clifford, and this is still classically simulable. So that gives you a whole array of new gate sets. So you get something. And then finally, sort of for the more maxi people, I wonder if it's possible to take this moment bound, which really looks like an instance of Weingarten calculus, like you see in the unitary group. And I wonder if we can take this and sort of boost it up all the way to a Weingarten calculus for the matchgate group, or sort of for the spin representations of the orthogonal group. And this is probably possible, but it's also probably quite hard, and it might actually be useful for some cool things. All right, with that, I'd like to thank you, and I'll see you at my sort of little in-person thing where you can ask questions. Thanks a lot.